interstellar Comet 3 I/Atlas has become a rare and fascinating target for astronomers as it makes its dramatic passage through the inner solar system, briefly disappearing from Earth's view while rounding the Sun. Although the comet is currently obscured by the Sun's intense glare, scientists and dedicated amateur observers have continued to monitor its journey using space-based instruments, allowing them to track its behavior almost right up to perihelion, the moment when it reaches its closest point to the Sun. These observations have revealed that Comet 3 I/Atlas is undergoing rapid brightening, offering valuable clues about its physical nature and how interstellar objects respond when exposed to the heat and radiation of a foreign star. Comet 3 I/Atlas is particularly significant because it is an interstellar visitor, meaning it originated outside our solar system and is merely passing through on a hyperbolic trajectory. Such objects are exceedingly rare. Only a handful have ever been confirmed, making every observation scientifically precious. As the comet plunged inward toward the Sun, it moved into a region of the sky where it became impossible to observe with conventional ground-based telescopes. From Earth's perspective, the Sun's overwhelming brightness drowned out the faint glow of the comet, effectively hiding it during one of the most critical phases of its journey. However, astronomers were not left completely blind, as several spacecraft designed to study the Sun and its surrounding environment were perfectly positioned to continue monitoring the comet. One of the most notable detections came from an unexpected source, a weather satellite. On October 18th, experienced comet hunter Wuricate Bunplod identified Comet 3 I/Atlas in images captured by the JWST satellite, operated by the U.S. National Oceanic and Atmospheric Administration. JWST is primarily intended to monitor Earth's weather and space weather conditions, but it carries an instrument known as CCOR-1, a coronagraph designed to observe the Sun's outer atmosphere by blocking the bright solar disk. This capability also makes it well suited for spotting comets that venture close to the Sun, and in this case, it proved invaluable. Bunplod reported that the comet was clearly visible in CCOR-1 data and appeared comparable in brightness to nearby stars with an apparent magnitude of around 11. In astronomical terms, magnitude is a logarithmic scale, and while magnitude 11 is far too faint for the naked eye, it is well within the reach of moderate telescopes under good conditions. Bunplod noted that the comet was moving steadily from left to right across the field of view relative to background stars and was expected to remain detectable by the instrument until around October 24th, when it would finally exit the coronagraph's field. JWST was not alone in observing the comet. Other spacecraft dedicated to solar science also tracked 3 I/Atlas as it approached perihelion. Among them is NASA's polarimeter to unify the corona and heliosphere mission, known as PUNCH. This mission consists of 4 small satellites working together to image the Sun's corona and the solar wind in unprecedented detail. While their primary objective is to study solar processes, their wide-field views make them useful for detecting transient objects, such as comets moving near the Sun. Data from PUNCH added to the growing body of observations documenting the comet's changing brightness and position. Another critical contributor has been the Solar and Heliospheric Observatory, or SOHO, a joint mission between NASA and the European Space Agency. SOHO orbits the Sun at a distance of roughly 1 million miles from Earth, stationed at a stable gravitational point that allows continuous solar observation. Its large angle and spectrometric coronagraph, particularly the LOSCO C3 instrument, has a long history of discovering and monitoring comets, especially those that skim close to the Sun. LOSCO C3 was able to follow Comet 3 I/Atlas until about October 26th, just days before perihelion, providing an extended observational record during a time when Earth-based telescopes were effectively blinded. The use of coronagraphs has been essential in this effort. These instruments are designed to block out the Sun's bright disk so that scientists can study the faint corona, the Sun's outer atmosphere. By suppressing the intense glare, coronagraphs also make it possible to see dim objects passing nearby, such as comets. In the case of 3I/Atlas, coronagraph data allowed astronomers to continue tracking the comet's trajectory and brightness even as it passed behind the Sun from Earth's perspective. As the comet approached perihelion, its behavior drew increasing attention. On October 28th, just one day before perihelion, two researchers published a study on the preprint server AR-14 reporting that Comet 3I/Atlas was undergoing rapid brightening. This phenomenon is commonly observed in comets as they near the Sun, but the details can vary widely depending on the comet's composition, structure, and origin. The intense solar heating causes volatile ices within the comet's nucleus to sublimate, releasing gas and dust that form a glowing coma and sometimes a tail. For an interstellar comet, whose composition may differ significantly from those formed in our solar system, such observations are particularly informative. The researchers estimated that at perihelion, the comet would reach an apparent magnitude of roughly 9. While this is still too faint to be seen with the unaided human eye, it would make the comet accessible to skilled amateur astronomers using quality backyard telescopes, provided it were visible in the night sky. Unfortunately, the geometry of its orbit and its proximity to the Sun at this critical time mean that direct observation from Earth remains extremely challenging. Nonetheless, the increase in brightness confirms that the comet is actively responding to solar heating and likely shedding material at an accelerating rate. The rapid brightening also raises intriguing questions about the comet's physical resilience. Some comets, particularly those that venture very close to the Sun, can fragment or even completely disintegrate under thermal stress and tidal forces. Monitoring changes in brightness can offer clues as to whether a comet is holding together or beginning to break apart. For 3I/Atlas, continued observations as it emerges from behind the Sun will be crucial in determining whether it survives perihelion intact or shows signs of structural damage. Beyond the immediate spectacle, the scientific importance of tracking Comet 3I/Atlas cannot be overstated. Interstellar objects provide a rare opportunity to study material formed around other stars without leaving our own solar system. By analyzing how such objects behave when exposed to solar radiation, astronomers can compare them to native comets and refine models of planetary system formation across the galaxy. Differences in activity, composition, and brightness evolution may reveal how common certain materials are in other star systems, and how they differ from those that formed around our Sun. The involvement of amateur astronomers alongside professional researchers highlights another important aspect of modern astronomy: the growing role of citizen scientists. Skilled amateurs equipped with the right knowledge and access to publicly available spacecraft data can make meaningful contributions, as demonstrated by Bunplad's identification of the comet in GOES 19 imagery. Such collaborations expand the observational coverage of transient events and help ensure that rare phenomena like interstellar comets are studied as thoroughly as possible. As Comet 3I/Atlas completes its close solar passage and begins to move back into a region of the sky where it can potentially be observed from Earth again, astronomers around the world will be watching closely. Space-based instruments will continue to provide critical data, while ground-based telescopes may soon get another chance to glimpse this visitor from beyond our solar neighborhood. Whether the comet emerges largely unchanged or bears the scars of its encounter with the Sun, its journey offers a fleeting but invaluable window into the diversity of objects that roam the interstellar depths. In the broader context of astronomy, events like this underscore how interconnected modern observation has become. Weather satellites, solar observatories, specialized research missions, and amateur analysts all contribute pieces of the puzzle. Together, they allow scientists to follow an object that would otherwise vanish behind the Sun, turning a brief disappearance into an opportunity for discovery. Comet 3I/Atlas may only be passing through, but the data gathered during its fiery swing around the Sun will continue to inform and inspire long after it has faded back into the darkness of interstellar space.